All right, and welcome to this video where we're going to talk about the divide and conquer algorithm design strategy, which relies on recursive code. And so we're going to start with some example algorithms that are ones that are fairly easy to understand and that similar to ones we've already looked at. We're going to look at search algorithms for searching for an element in a list, but we're going to look at them from a recursive standpoint, which is maybe slightly different from the perspective you may have looked at them in the past. So the first thing I want to remind ourselves is of the difference between our normal sequential or iterative programming and what we might call recursive algorithm or recursive programming. In a recursive algorithm, the main characteristic that makes it recursive is that it is a function or a method that calls itself. And so usually that means that our recursive algorithm is going to be composed of two components. The first component is going to be what we, in the recursive algorithm case, we sometimes call the terminating case, are going to be the simple cases, the easier cases to solve. And we're going to solve those ones maybe using a brute force algorithm, or maybe just hard coding the solutions in if they're that easy to solve. But then all other cases we're going to rely on using the recursive case, and that's where we split the recursive case into sort of smaller pieces, and then we solve those recursively, and then usually we need to put those pieces back together in some way. And so we call this design strategy divide and conquer. Divide and conquer is a strategy used in computer science very broadly in all kinds of different areas. The idea that led to proceduralization or object-oriented programming is also a principle of divide and conquer, and we see this a lot, that if there is some particular component of your program that is getting too complicated, then usually the wisdom is to split that into smaller pieces that are easier to work on. And of course, so this principle is ubiquitous in computer science, and that is the principle we're applying here, but it's also the name of a very specific divide and conquer, or sorry, a very specific algorithm design strategy. Divide and conquer divide and conquer is both a broad principle but also a narrow algorithm design strategy, and that's what I want to focus on here. So we're going to take a look at that, and to do that I want to look at two different problems again that we're probably very familiar with, the idea of searching an unsorted list and searching a sorted list. Again, I just want to maybe focus here that I've stated these two problems in a formal way using the language of formal mathematics, but also using the principles of computer science that states that an information processing problem is going to be a relationship between an input and an output. And so we're gonna take a look here again at these two problems in this way. We notice that they have similar inputs. Let's look at them in turn. For the first problem, searching an unsorted list, our input is going to be a list of integers, a from 1 to n, and t, a target integer that we are looking for. One comment that I'll make here is you'll notice that I've assumed that our indices start at 1 and go to n. This is an assumption that while we operate here on the level of problems and algorithms up in the realm of the abstract, it's actually more convenient for us usually to index our arrays or our lists from 1 to n, as makes sense, since that way it clearly has, say, n elements in it, which is obviously a little bit different if we index from 0 to n minus 1. Because we don't want that little minus 1 showing up in our math here and there and so on, we've decided to change our indices here. And of course, we could have redefined this using 0 and n minus 1 and nothing would have changed here. It would be functionally the same problem, of course, assuming we change the output to match. All right, the one distinction I'll draw here between the searching an unsorted list here and searching a sorted list is we've added an additional criteria or condition to the input. In this case, we're saying that the elements in our list are actually, it says here, in, well, I guess non-decreasing order. All right, the potential for equality, but in increasing order if they're not equal. So if we assume they're distinct, then this would be in increasing order. So this creates a new problem then. A new problem. In our original one, the list could be in any order. In our new problem, it has to be in this non-decreasing order. But both of our problems have the same output, which is either we want to know the index of an element that is equal to our target, or if we don't find such an element, give me -1, which I've chosen to just be sort of a sentinel error code here. We could have, again, selected anything. Since we started our index at 1 to n, we could have selected 0 here as well. That would have been a perfectly fine error code. Or if we really wanted to, since we, again, are operating on the realm of problems and algorithms, we don't need to think in that sort of maybe we're thinking here we're constrained to the type, the return type of our output. Nothing in the realm of problems constrains us to that type. If we wanted to here, I could return, in the other case, I could just return error, but whatever that means, or I could return false. That might be a good, a better error code telling you there is no such target. So here I've just selected -1, but again, on the realm of problems, we could have many different definitions of this problem that would be functionally similar, and so the differences between them we should not be too sensitive to. All right, as I mentioned, I want to use these problems to present our divide and conquer strategy. So I do want to spend a moment or two here just talking about the design strategy itself, going one step at a time. And so here I've got it listed as sort of a 5-step process. And let's take a look at each of these steps in turn. So the first step is actually a very important step. This step is, it says here, state the problem as formally as possible. So the notion of formalism here is the idea of using mathematical formalism, the tools of mathematics, maybe the language of set theory, as we see sort of down here below in this problem we've already stated. And so the first important step is to try and isolate the problem you're trying to solve as clearly as possible. And maybe to emphasize this, I want to bring up another algorithm that you may or may not have heard of before. This is sort of a humorous algorithm coined by von Neumann, but it shares a similarity to our design strategy. Now, John von Neumann, whom hopefully you've encountered in your studies before, is a very important figure in computer science. We'll see in a future video here, one of his contributions is he is cited as the founder of the merge sort algorithm. I mean, he probably wasn't the first one to actually consider that merge sort algorithm, but he was the first one to consider it in a computer science context and write it down for us. He's also the namesake of the von Neumann architecture, which is the standard computer architecture that we use today, and he was the developer of that. But von Neumann's algorithm is sort of a humorous algorithm. He claimed that this algorithm could solve any problem, and it has a couple steps here. And the first one is write down the problem. And that maybe makes sense. That was the same as our first step here, right? Our first step says state the problem as formally as possible. Now, the rest of the algorithm, I think, maybe only works if you're John von Neumann, but the next part is going to be think really hard. Yeah, and then the third bit was, well, now you can write down the solution. Now, again, maybe this works for John von Neumann. Maybe you're smart, so you can think really hard. But one of the reasons why I do like to bring up this particular example is that I'm going to, in most of the algorithm design techniques that we're going to look at in this series, there's going to be some part of the problem, there's going to be some part of the technique where we have to think really hard. And so what I want to sort of emphasize here is this part is creative. So we need to think, how can we bring some of that creativity into our algorithm to make it actually work well? We're not going to just have a recipe that's going to work for any problem. Now, why not? Now, why don't we have a recipe that works for any problem? I'd like to have a recipe that works for any problem. Wouldn't that be good? Well, part of the problem is, again, this creative bit. We don't really know how to encode the creative bit into a program yet. We don't have a way to do that. And maybe we're working on it. Maybe that's an artificial intelligence type of problem. But maybe the other answer to this question is if we did have something to fill in this part, if there was a way to algorithmically fill in this part, well, then a lot of our jobs as computer scientists probably would go away, as computers would be programming themselves, which would be great. They'd be solving the problems automatically, and maybe one day we'll have machines doing that for us, but at the moment we still need to figure out this part 2, this creative bit. That's up to us, the humans, the computer scientists. So again, that's part of the reason why we've got our divide and conquer design strategy is going to be one of the tools in our kit to fill in that step number 2. All right, so let's look a little bit closer now at our design strategy. Our design strategy has 5 steps, not like von Neumann's. Although like von Neumann's, we've just added a couple extra steps here. So the first one was state the problem as formally as possible. The next step is to identify subproblems. And we probably have some intuition of what that means already. I'm going to flesh that out a little bit before we get started. Step 3 is where the creativity comes in. This is the trickier part. This is where we need to be a little bit clever. And here it says find and prove correct a self-reduction from the problem to one or more of its subproblems. And I'm going to focus in this series on this step 3 over and over again. We're going to probably see a good half dozen or more problems where we're going to try and find this relationship between the problem to one or more of its subproblems. And again, I'm going to flesh out what this means in a little more detail. All right, if we get over the hump of step 3, which again is where the creative bit is, where we need to be clever, then step 4 and 5 actually are just fairly straightforward as long as we follow the steps involved and then again apply some mathematical tools. Maybe again with a little bit of practice those should become straightforward as well. So again, step 4 here says, well, now design a recursive algorithm from the structure of the self-reduction. And we'll see in a second that a self-reduction has a recursive structure. And so in fact the algorithm is very simple to read right off of the self-reduction. So once we have it, the algorithm comes almost for free. We just sort of copy it down, that's one of the good parts. And then secondly, we're going to need to, or step 5 I guess on our list here, we're going to need to analyze the runtime of the algorithm, and we're going to use a mathematical structure called a recurrence relation to do that. And most of the next couple videos we're going to focus on tools for number 5. All right, so as it says here, we've already carried out step 1, which is stating our problem as formally as possible. And so we have here one problem, and we saw this, we had 2 on our previous slide, 2 problems stated as formally as possible. So we're really going to want to focus in on step 2 and 3 now, and that's where I want to go next, is to talk a little bit about the notion of what a subproblem is. So to define what a subproblem is, we're going to do this in terms of what a subinstance is. So recall that an instance is just specific input to the problem. So in the previous slide we had the input stated generally, a list 1 to n. Well, here I've got a list, a specific list with entries 1, 2, 3 up to 7. Now this is a special list. It's actually in ascending order. So that means it is a good this is an instance of either of the two problems that we've looked at so far, searching an unsorted list or searching a sorted list. In this instance, we have the example of searching the list for the target 8, which we can quickly see is not in the list, so this would be an instance for which we should return -1. We can restrict the instance. I've restricted the instance in this case by removing the first element. And this gives me a sub-instance. I could search this smaller list for the target as well, and maybe the answer, the solution that I get from that, might help me solve the main problem. So for instance, in this example, maybe I search this list for the 8, find out it's not there, and then I also compare the 8 to the 1 and I find out they're not equal. That might be sufficient for me to say there's no 8 in this list. Again, if we were to do this recursively, we might go smaller and smaller. We might take the 2 off next, the 3 off next, and get smaller and smaller. There are other ways to restrict the list. In some cases, we might want to throw away half the list. So here I've thrown away the first half, done it again, and then we're down to only one element in this case after throwing away half the list twice. These are just examples of ways to restrict the instance of a problem to give us sub-instances. Well then, if we write this more generally, we can restrict the general problem to get a sub-problem. So here, maybe a sub-problem, instead of going from indices A to B, we might go from A plus 1 to B. Here, M maybe is not defined, but maybe we can define M to be some middle element. And then again, we might have our sub-problem being from A, M plus 1 to B. Now these two sub-problems correspond maybe to the sub-instances that we looked at above here. So when we're going to be characterizing our problem, characterizing it or trying to solve it in terms of sub-problems, we're going to use this kind of formalism to identify our sub-problems. All right, I think we're almost ready to define our self-reduction, which again is a relationship between the main problem and its sub-problems. But to do that, we need a way to actually express this relationship. And again, this means we might need a mathematical formalism here. So let's do this together. And I'm going to define this UAB to be the output, the expected output for our problem if we were trying to search for the target between A and B. Now here, I haven't included the target T. We've got some target T here. I haven't included it in my description here. I'm going to just assume we know what T is. It's part of the input, but for simplicity, to save ourselves some save ourselves some writing here, I'm not going to write T. We're never going to change T, so I'm just going to leave it as it is. And now again, what UAB is meant to be is the output of the problem searching for element T between indexes A and B. Now, if the element T appears in that sublist between A and B, we should return the index that it appears in. If it does not, we want to return the appropriate output here, which would be -1. Now here, you'll notice one thing I've done here is I've changed from 1 to n. We were describing our problem earlier as 1 to n. I've changed it to A to B. Now, why have I done this? Well, this is so that we can, well, there's two reasons. One is so that we can start referring to subproblems, and we saw here we could have A plus 1 B. That might be a subproblem, so we might write that U A plus 1 B. Okay, that would be a subproblem. And another reason is that's important here is remember that our output for this problem is supposed to be one of these elements, or possibly a -1. So maybe I'll write that like this, union -1, if the element doesn't exist. Now, what's important here is if I've now taken my array, and over here this is index 1 and this is index n, and I now want to search this subarray here, which let's say it starts at n over 2 plus 1. This subarray here, if say I find the element and it's in this location, I want this element, I want this index to be returned out by the final algorithm, this index here, which whatever it might be, let's say it's 3n over 4. If instead I renumber my indices here from 1 to n over 2 on the next time, I'm going to lose the actual index that I'm looking for here. So that's why I'm changing from 1 to n here to a to b, so that when we move from one problem to the subproblem, we preserve the indices from the original list, so that if I return back index 5 from some subproblem, that meant index 5 in the original list as well, in the original list, so that we don't have to convert that as we go. So I'm going to leave that here in terms of a and b. And now what I want to do is I want to define what is this going to be equal to in a recursive way. A self-reduction is recursive, and it's going to have a couple components here. And to do that, maybe what we should do is think about some subproblems, some easy subproblems that we might consider. So one of the easy problems, now remember here my a and b are the indexes that I want to search. And usually we're going to assume a is the start and b is the finish index. We want to search the subarray between those two indexes inclusive. So that means we usually want a to be, our assumption then is a should be less than or equal to b. That makes sense. Otherwise, let's consider a case here, a greater than b. In fact, this is the first case I want to try here. If a is greater than b, now this is a weird case. Why would this happen? Maybe whoever called our function called it on bad input, so maybe they messed up. Or possibly, and we haven't got here yet, but maybe one of our recursive calls, is going to be changing the indices. Maybe it's gone ahead and changed a. Remember, we had one possibility, a plus 1 b was a subproblem we might look at. What if a was equal to b, then that would put us in this case here. Okay, so what does that mean? That means we're actually trying to search an empty array. Okay, and if we're trying to search an empty array, we know by definition of our problem there's no element in there, our target's not there, so the right output is -1. So if a is greater than b, I'm going to return -1. So that handles this special case here that seems like it's an error but might occur due to recursion. So now we're just going to focus on this case here where a is going to be less than or equal to b. Maybe there is a special case where a is equal to b. We might, it's not wrong if we consider that case, but I'm going to consider the other two cases here. But there are two cases that I want to consider. Now here I'm trying to solve the problem. I want to find a relationship from the main problem down to its subproblem, and I want to think about what searching a list usually looks like. Say this is my index a that I'm starting on here. In my normal iterative loop, if I could just use a good old loop, a for loop, I would start here at index a, and I would check to see if this is t or not. So, is this equal to t? Right. If it is, great, we return it. If not, what do? We continue our search over here. We would move our loop on. And that's the idea that I want to do here as well. So I want to consider something else here. Let's say, what happens if a sub a, not I, is t, the element that we're looking for? If it is, then a is the index it belongs in, so a should be the answer that we return. Okay, so then that leaves us with another case here. Well, what if a sub a is not equal to our t? If it's not equal to our t, this is where we need to get recursive, and this recursive call might be useful to us. Now, in fact, this is what we're going to write down. So let's just copy it over here. There's going to be u a plus 1 b. But let's confirm and make sure that this makes sense to us. Is this actually correct? Now, what does this express? This will tell us the output if we searched from index a plus 1 to b. Okay, now we've already confirmed here that the target element is not the element in position A, if this recursive call here, if this recursive subproblem comes back and says -1, then that means it's not in position A plus 1 to B either. So we know, we have confirmed it's not in position A to B. So the right answer here is indeed -1. So again, if this subcall, this subproblem says -1, then the right answer is -1. If this subproblem does not say -1, it selects an element between A plus 1 and B, then it's giving us the right answer. That is, it has found the target element, right? In one of these calls, it's found the target element, and so we should also return that same index back. So indeed, this is the correct answer in this recursive case. All right. So this is our first example of a self-reduction. And again, we can maybe see this here on the slides. I've got the same example here. This self-reduction allows us to create effectively an algorithm for a recursive algorithm for searching an unsorted list. And here I've got just stated here, if we actually create this algorithm, very much like our standard sequential search for using a loop, this recursive sequential search is a linear search, meaning it's going to result in a linear number of operations, or big O of n number of operations. And we're going to take some time to look at that in more detail. But let's take again a look at our second problem here, or another problem here. Okay, so to continue here, I wanted to reflect on what it means to find a self-reduction. If you find a self-reduction for a problem and you confirm it's correct, we confirmed it correct sort of verbally, we didn't prove it correct, but if you can confirm its correctness, then we say that the problem has what we call optimal substructure. And that means if a problem has optimal substructure, it has this relationship from the main problem to its subproblem, this self-reduction, then we can design a divide and conquer algorithm for it. And this divide and conquer algorithm, and that's what we're going to look at here more in a second, is going to have this recursive structure similar to that of the recursive structure in the self-reduction. Usually for a particular problem, there's going to be more than one way for us to come up with a self-reduction for the problem, which is usually good. That means there's more than one algorithm we can develop for it. And in some cases, some algorithms are going to be better than others. Here, I've presented a second self-reduction for our problem. Again, this is still searching an unsorted list. This self-reduction is somewhat inspired by binary search, in the sense that I'm going to select a middle element here, m, and maybe we can verify here in a moment that this will be the middle element if we have indices a and b. It might be a worthwhile exercise to go verify that. But we're going to take that middle element, and like a binary search, we've got similar setup here. Maybe I'll just go a little slower here. We've got a similar setup as our last self-reduction. If we're searching an empty list, a list with 0 elements in it, we know our answer must be -1. But the change we're going to make now, instead of looking at the first element, a sub a, we're going to look at now this middle element, a sub m. And if we find the target element there, like a binary search, we're going to return that index, and that's sort of our lucky early termination. Otherwise, if we don't find it, now we don't just have the remaining of the list to search. We still have to search the remaining of the list, but because we looked at the middle element, we now have sort of a left half of the list and a right half of the list that we need to look at. So here I've got this recursive call, or this subproblem says, well, now go look in the left half of the list and see if it's there. And this one here says, well, now go look at the right half and see if it's there. And I've chosen to combine these two using the max operation. Now let's just verify and make sure that that's correct, and let's see what really happens here. Well, if both of them return -1, right, then the whole thing will return -1. And again, that will be correct. We didn't find it in position M. We didn't find it in the right. We didn't find it in the left. So we should return -1. Okay, first condition, check. What if one of them returns -1 and the other doesn't? Meaning we don't find it in one sublist, but we do find it in the other. Well, since -1 will be less than any of our indices, we're guaranteed to return the correct answer here as well. So the only thing that maybe stands out, what happens if this one returns an index and this one returns an index? We find it in the left and we find it in the right. Then it looks like we're going to return the index of the greater one, which means in the case where there's ties, where there are more than one element where we find the index t, we're gonna actually end up returning the maximum index. Notice this is the opposite of our last problem. If there were ties in the last example, we would have returned the first index that we found, meaning the smallest index. Okay, this is another self-reduction for our searching an unsorted list, where we sort of split the list in half and we search its right and its left. And we might ask ourselves, well, which of these recursive algorithms is better at searching a list? And we don't really have an answer yet. We want to develop some technique to do that. So maybe we haven't actually had an opportunity to do that for this problem. So we'll come back to that in another video. But continuing here with this video, I want to maybe again pivot to now the idea of doing a self-reduction for a problem for searching a sorted list. Remember that searching a sorted list gives us the advantage that now our elements are in order. And so we can do like a dictionary search or a phone book search, where we can look, you sort of start in the middle and then see, am I in the left half or the right half relative to the current element I'm looking at. So again, let's see how we can structure that using this self-reduction formalism that we're investigating here. We've got, again, our search a sorted list problem. I'm now going to use S to express the output, and I'm still going to use the AB index formalism that we've been using before. I'm going to still have to define our M term in the way we did in our last example to find the midpoint. And then I'm going to search here, same as before, our output of -1 if we're searching an empty list, if A is greater than B. And then again, we're going to look at that middle element. If it is the target that we're looking for, we return that index. Otherwise, we have to do a search. Now, very similar to the last example. In the last example, we had these same two subproblems, the left and the right. But in the last example, we had to search both the left and the right because we had no indication of which side to search. But with binary search, we can now compare and say if the element we found in position M, if it's less than the target must be to the right of this position. So we will search from position M+1 up to B. We don't need to search position M again. We've determined it's not there. Likewise, if the element we found in position M is greater than the target, if our target exists, it must be on the left-hand side. So we'll search on the left-hand side. And again, hopefully, some earlier analysis of binary search has allowed us to see that this is indeed a logarithmic search. And again, in another video, I will present analysis that indeed shows that this self-reduction leads to logarithmic runtime if we develop that reduction. All right, so to sort of finish off here, we haven't completely finished. We've been working on step 3, that creative component, where we find a self-reduction relationship from the main problem to its subproblems. So going back to the first self-reduction we found, which is this one here, we can now do step 4, where step 4 says sort of read the recursive algorithm directly from the self-reduction that we've created. So here's our self-reduction. Let's see how almost deliberately we're reading this. So here we're setting up our recursive algorithm. We've got our input now expressed more verbosely with the whole input, A, the input list, T, the target we're looking for. And then all we're really doing is translating these into code. So if A is greater than B, so if A is greater than B, return -1. All right, great. If we find the target in the first index, if we find the target in the first index, return A. Great, okay. And then finally, the last one, we just have to realize that this reflexive definition where U is defined in terms of U itself is in fact a recursive call. So now here, if we're in the last case, we need to return, okay, sequential search, that's a recursive call, on our restricted subarray. So here our index has changed. We now will only do the subarray from A plus 1 to B. We can actually take this code, and in fact we could do this directly with the self-reduction too. We can take this and use this to come up with a recurrence relation to express the running time of the algorithm as well. Now a recurrence relation here, we use t for time, is a recursively defined mathematical function that's going to tell us how many operations are carried out by our algorithm when run on input of size n, our input list here of size n. So to do this, we're going to actually have maybe two different cases here, and we'll consider them in turn. I'm going to start with if n is less than or equal to 1, and this is sort of our terminating case or our base case. If we have a small sized list, 0 or 1, we know that we're going to actually terminate with a small number of steps. How many steps is not really that relevant as long as we note that it's going to be a constant. So I'm going to call that C. The next case that we want to look at here then is going to be for our recursive case if n is greater than 1. And here again, thinking of the worst cases when we actually have to recurse. Here we're actually going to have two terms here. One, I'm going to say my recursive term, and then the other one is just sort of the extra work. And here the extra work is any other iterative work that we do. Iterative meaning if we use a loop or something here. We actually don't do too much extra work in our example algorithm here. All the extra work is just carried out by our checks. So is A greater than B, is the element in the location, and a little bit of arithmetic going on as well. And so all of that amounts to just another constant amount of work, and I'm going to call that D. So that remains to say, well, what about the recursive work that gets done here? Well, in the recursive case, we're going to make one recursive call. And how much time that recursive call takes is going to be expressed here in terms of t. Now, the thing we need to recognize is the size of the size of the call that we make is 1 smaller. So in our recursive case, when n is greater than 1, we're going to make one recursive call here. There's sort of an invisible 1 out front here. We make one recursive call of size n minus 1, and then we do a constant amount of extra work. So we can call this self-reduction, or sorry, this recurrence relation here, expressing the runtime of our algorithm. And again, I've got that stated here as well. So again, with this self-reduction, we can do sort of step 4, which gives us the code, and the very first bit of step 5, which or maybe 5.8 or something like that, is to come up with this recurrence relation, and then we need some techniques to find a theta bound for this recurrence relation. Okay, so to complete this video, I want to just do this last little step with our other two recurrence relations. So the first one we had here was also for searching an unsorted list. Now these two have a little bit more overhead because we do have to deal with this middle element m. So we have to calculate where m is. So when we take a look at the code here, we'll see it's not immediately just copying over. The first line is still the same for our base case. But now we have, what about in this case? Well, we still need to know what m is. So the first step is calculating what m is. Then we can go into this case to compare it against our target element. If we find it, good, that's early termination. And all I've really done here, since I'm going to put it through the max operation here, I've just pulled them out and made two sort of internal calculations. We've done one recursive search to the left, oops, to the left, that's the second one, one to the right, and then we take the max of the two. Again, we can come up with a recurrence relation here to express this. The key thing is that we're making two recursive calls, and the size of each one is about 1/2. And I'm going to be a little more precise than that. We made two recursive calls, and the size, as I said, is about 1/2. Well, more precisely, they're upper bounded by the floor of 1/2. Since we've deleted out that middle element, the floor of 1/2 is a good estimate. So remembering that we need to have an integer in here, so the floor will help us convert that to an integer. Okay, so we do want to analyze this recurrence relation as well and come up with a good theta bound for it as well. Well, that will be in our next video or two. All right, let's look at our final one. This was our binary search self-reduction. And the binary search self-reduction has had 4 cases to it. Again, similar to the last one, we still have these 2 recursive calls, the left or the right. The critical point here is that we only have to do one or the other, and we'll see that here in a second. The code is maybe not too much different or not too surprising. We still need to calculate our m, otherwise the cases are the same. Again, noting we're going to do one of these recursive calls or the other, unlike our previous case. So we're still going to have that same self-reduction, except now, so we're going to have the same sort of recurrence relation, but now that 2 disappeared, because we're only going to do one of these calls or the other. And luckily, because of that 2 disappears, that's what's going to allow us to see that this is indeed logarithmic, where our other algorithm will not be. Okay. So I do want to complete this, this video here with one final comment and foreshadowing for our next video. Well, what do we do with a recurrence relation like this? Well, there's actually going to be a couple techniques that we can apply to come up with a good tight bound for this. And then prove it correct. Now, proving it correct is maybe the easier one at the moment. Is we're just going to use induction to prove it correct, and perhaps you've had an opportunity to do that and then earlier with earlier math examples. I'm now going to include in the next couple videos, or a good handful of videos at least, examples of how to prove these true with induction. However, before we get there, I'm going to use a technique to come up with a good guess, a good theta bound. Before we can prove the bound is correct, we need to know what bound it is. For this one, we maybe know binary search is logarithmic. We could maybe skip over step 1, guess that it's logarithmic, and go straight to the induction. But in my next video, I want to present the recursion tree technique, where we're going to do an analysis of the recursive tree, the recursive structure of the tree, of all the recursive calls, and analyze how many operations are going to be carried out in each of those calls, and more specifically on each of the levels. So that's what we're going to do in our next video, so please stay tuned for that. Thanks for watching, and we'll see you in the next video.